Hey guys, welcome to part 7 in this Bitcoin Cash wallet tutorial. In this video we're gonna complete the implementation of the withdraw function that we started off in the previous video, and we're gonna make sure that it is able to handle every corner case that we want where we want our wallet to send money to different types of outputs. By the end of this video we're gonna have a fully functional and complete Bitcoin Cash wallet that interacts with the real network and is able to send and receive real money. So that is it for the intro, and let's jump right into it. First of all, I'm gonna open the wallet.js file at the same part where we left it off in the previous video. As we can see, we hard-coded a value for the transaction fee at 250 satoshis, which worked fine for this very specific case that we tried in the previous video. However, it won't work for many other cases where we want our wallet to also be able to withdraw. The reason for this is in the Bitcoin Cash network, whenever you're creating a transaction, you need to provide a miner fee which is at least equal to 1 satoshi for every byte that conforms the transaction. That means that the bigger the transaction itself is, the bigger the fee needs to be for miners to actually relay it and actually mine it. That means that this 250 that we have hard-coded here actually needs to make sure that it is big enough for the transaction that we're creating here, and we also don't want to overpay, since when we put a fee which is exactly the same number of bytes as the transaction, that is good enough, so there's no need to overpay here. The first thing that we need to do to fix this problem is, instead of using a hard-coded fee, we're going to create a function here which is called estimate transaction size, transaction bytes, let's call that like that. And this function is essentially going to try to figure out what the size in bytes is going to be for the transaction at the end of this process. Now, because of the way the transactions themselves are created, that number is actually dependent on a couple of things. Like I said on the previous video, whenever you're creating a transaction, what you're doing in the end is just you're consuming outputs and creating new ones. Each one of the UTXOs that your wallet has become inputs to the new transaction, and outputs are the recipient address that you choose or the user chooses, and sometimes you have a change address which sends back any leftovers back to you. Now, the reason why the code that we have here definitely doesn't work in many cases is, for once, it may be the case that you're actually sending money to sending money to an address for an amount which is pretty much all of your balance. In that case, you wouldn't really have any change coming back to you. So we need to make sure that our wallet can handle that case. Another problem with this, with the current implementation, is that if you ever try to spend an amount which is greater than your balance, then this code will fail, whereas we would actually want to send a very clear message saying, hey, what you're trying to do is not possible because you have insufficient funds. So in order to estimate the size of a transaction, what we need to know is we need to know exactly how many inputs and how many outputs our transaction is going to have. Each input, which is a UTXO, which exists in the network for our address, actually you need to prove ownership for each input if you're trying to spend it. That means that each input by itself adds to some overhead in the transaction size. The same goes for outputs. Each output that you define contains, among other things, the hash of the public key, or namely the address to which you're sending money to. So this function that we have here necessarily needs to have at least two arguments. I'm going to write the function down here. And the arguments that this function needs to have are the input count and the output count. That means input count is essentially how many UTXOs I'm consuming, and output count is how many outputs I am creating. Now, the formula that we're going to use to estimate the transaction bytes based on these two parameters is actually it's quite simple. I'm going to write it down right now. These magic numbers that I'm writing down in this formula are actually derived by a very low-level detail look into how inputs and outputs are created in a transaction. To actually derive these numbers right now would require us to delve into low-level details about Bitcoin script and how these types of inputs and outputs are created. So we're not going to do that. I'm going to leave a couple links in the description so where you can see a more detailed analysis on how to come up with these numbers. But I will say from a high-level overview what these numbers actually mean. In the first case is 149. What that actually means is each input is going to consume roughly 149 bytes. The reason for that is each input, like we said before, needs to provide a digital signature generated by the owner of the private key, which relates to that address. That signature itself amounts to a certain amount of bytes, which is usually 71 or 72 bytes. It's actually variable because it depends on the there's a random chance that you're going to get one length or the other one, but it's roughly 70 something bytes. At the same time, like we said a couple of videos back, whoever's trying to verify this transaction needs to have the public key which is related to the address where the money was sent to. Because of the way that outputs are created, where you don't really embed the public key of the person receiving the money, but instead you embed a hash of the public key. Miners actually do need to have the public key by the time that they're verifying. That means that instead of providing the public key at the time when you create the output, you actually need to create it when you're spending the output. That means that the public key for the address where the funds are located needs to be provided as part of the input in the transaction that is trying to spend them. That also adds up to the 149 bytes. Now there's other pieces of data that need to go into an input, and all of that together sums up to a little less than 149. That number is variable. It depends on the input itself and on the signature length. But there's also some metadata, and 149 is a value that we can use to overestimate a little bit the size of each input so that we make sure that we never pay less fee than we actually want. In the case of the outputs, the number 34 is actually comprised of, like I said, some metadata that also forms part of the output. But the most important part is actually just the hash of the public key to which you're sending the funds. That means essentially the address. So each output itself needs to contain the number of satoshis that you're adding to that output, and at the same time it needs to have the address to which you're sending the funds. That last number 10 at the end is just the sum of various metadata fields which are embedded in a transaction. Again, to actually know what those 10 bytes are made up from, we will need to look into very low-level details as to how a transaction is built on a binary level. All of these are going to be linked in the description of this video so that you can take a closer look if you're interested. Going back to the withdrawal function, when we're trying to estimate the transaction bytes for the transaction we're about to create, we actually need to compute two different types of fees. And the reason for that is that by the time we're trying to construct the transaction, we're actually not yet entirely sure how many outputs our transaction is going to have. For example, if you're sending money to a certain address and there is change left over, you're going to have two outputs, one going to the other address and the rest going back to your deposit address. If you're trying to spend just by chance the entirety of your balance, then you're never going to have that change output because you're essentially sending everything to that other address. So that means that there are cases that we want our wallet to be able to handle where where we're gonna have one output and cases where we're gonna have two outputs. So we are going to compute here the two possible fees that we're gonna do here that we might need in the future. First of all, the number of inputs is defined by the UTXOs, which we have right up here, and that is exactly the inputs that we're going to be adding to our transaction. So that amount is always the same, which is just the amount of UTXOs that we have. And I'm going to create two variables, fee1 and fee2, and these fees essentially mean what is the minimum fee that we need to pay in order to create a transaction with UTXO's length number of inputs and either one or two outputs. Just a comment here. There seems to be a problem with units at first, because on the right-hand side we have an amount which is measured in bytes, whereas on the left-hand side we have variables which represent numbers of satoshis. So the reason why we can equate these two things is because in the Bitcoin Cash network, the minimum fee that is needed for a miner to relay your transactions is exactly 1 satoshi per byte. So technically what we're doing here is we're multiplying the number of bytes that our function estimates times the quantity 1 satoshi per byte. So that means the units actually do add up, but we don't need to explicitly make that calculation, since just 1 satoshi per byte will suffice. If you actually wanted to put more than 1 satoshi per byte, you could do that here, like for example putting 5 satoshis per byte. So multiplying essentially the amount that we calculated as the number of bytes in the transaction times 5. You can see at this point how you could build a wallet which also provides you the possibility of provides the user the possibility of choosing what number of satoshis per bytes they want to use in their transaction. In the case of the Bitcoin Cash network, 1 satoshi per byte is always all that is needed, so there's really no good reason to actually implement this. Now, the first thing we want to do once we have these two values is we want to make sure that we actually have enough money to do a transaction at all. So the way we're going to do this is, first we're going to check whether the balance that our wallet has minus the amount that we're trying to send is bigger or smaller than the fee with a single output. So something which should be obvious by looking at the formula for estimate transaction bytes is that the greater the number of outputs, the bigger the value. So fee1 is always going to be smaller than fee2. That means that if the balance minus the amount that we're trying to send is less than the smallest possible fee that we could ever want to use, which is a fee of having one output, that means that there is no way that we can ever spend that money. So if that is the case, then we can most definitely throw an error here saying that we have insufficient balance. So if that error doesn't get thrown, that means that we're definitely going to be having a transaction going on there. So we can actually leave these two lines untouched, because after that point we're going to be sure that we're going to be using those, essentially creating a transaction from our UTXOs. The things that can change now are the outputs themselves. That means that after the definition of the outputs, the rest of the code will also stay the same. The part that we need to define here is which are going to be the outputs that we're going to be sending. So in order to actually figure this out, the first thing that we need to do is we need to think whether we're ever going to have a change amount or not. That means given our balance, if you subtract the amount that you're trying to send, do you have enough satoshis left to actually send them back to yourself as a change amount? And the way you do that is you need to ask whether the balance minus the amount minus the fee with two outputs is greater than equal, or so the most intuitive thing would be to say if the balance minus the amount minus the fee with two outputs is greater than 0, that means that I actually do have some leftover money. However, there's an additional restriction in the Bitcoin Cash network, which is that you cannot create an output which is smaller than the, essentially you cannot create an output if by the time that you wanted to spend that output, you would need to spend 1/3 or more in fees. That essentially produces what is called, prevents what is called dust outputs, which essentially means really small amounts of money deposited in UTXOs that would be just too expensive to spend. So the way this is handled is you need to actually make sure that any outputs that you create are greater than the dust amount. So in order to complete that, I'm going to create a constant here, which is called the dust limit. And this dust limit is going to be, you can actually calculate this, which ends up being around 550 Satoshis. We're just going to use the number 600 to be on the safe side. So now the if that we were writing before is completed like this. We want to check if the balance minus the amount we're sending minus the fee with a transaction of two outputs, if that's smaller than the dust limit, that means that we cannot afford ourselves to send back some change. That essentially forces us to have a single output transaction which sends the amount that the user chose to the given address, and that's essentially all the outputs that we're going to have on that transaction. If we added an extra output to that, we will no longer be able to pay the fee for two outputs. Otherwise, if it is not the case that that amount is smaller than the last dust limit, that means that we actually do have some leftover money that we want to send to ourselves. So the way we would do that is we would add the same output that we had before, and we would add the change output, which goes to our own deposit address, and the amount that we're sending is the balance minus the amount minus the fee with two outputs, because in this case the transaction is actually going to have two outputs, so we need to pay for both of them. However, there is one small catch here, is what happens if the user inputs their own deposit address as the destination address for the withdrawal. In that case, there would be nothing wrong with this code. However, we would be creating two outputs with the same address as destination. So given that would be wasteful, we're going to add a small amount of code here to make sure that if the address we're sending money to just happens to be the same one as our own deposit address, we are going to have a single output which sends essentially all our money back to ourselves. Just one small catch here is this address is actually taken from user input. And if you might have noticed that Bitcoin Cash addresses sometimes are prefixed by the Bitcoin Cash prefix and sometimes they are not. This is optional on most UIs. So in order to make this check a little bit more robust, we're going to check whether a normalized version of this user input address is equal to our deposit address, which is already in this normalized format. The way that we do this is we create a new Bitcore address passing in the user address. Then we just create a string out of it which returns the normalized version of the string, and we compare that to our own deposit address. If it is the case that this is true, then we have a single output which goes to our own deposit address, and the amount that we're sending to ourselves is essentially our original balance minus a fee of a single output. We're using a single output here because we're using the fee for a single output because if you take a look at the resulting transaction, it's going to have just a single output back to ourselves. Otherwise, if the address we're sending the money is not exactly the same as our deposit address, that means that this is essentially the same type of transaction that we were dealing with on the previous video. That means we have a different address we're sending a certain amount to, and then we need to send ourselves the change amount, which is the original balance in our wallet minus the amount that we're sending minus the fee that you need to pay for a to-output transaction. So that mostly completes all the border cases we wanted to handle. We also need to check one more thing that we didn't add here, which is what happens if the user is trying to send an amount which is smaller than the dust limit. That is also some validation that we need to do to make sure that the user's transaction doesn't fail by putting a number which is too small. So the way we're going to do that is if the amount we're trying to send is smaller than the dust limit, we can just throw an error which says something like output amount below dust limit. So the code as we have it right here, first we check whether the amount is below the dust limit. If it is, we fail. Then we check whether we have enough balance to create any transaction at all. If that is true, then we continue to create a transaction from our UTXOs. And then we split the logic into 3 different cases. The first case at the top is where we have a single output of all the money going to a single address with no change amount. The second case that we're dealing with is when we are sending everything to ourselves except the fee for a single output transaction. And then the third case is when we're sending a certain amount to a certain address that the user inputted, which is different from our own deposit address. And we're also paying, sending the change amount to ourselves. So those cover the 3 cases. In the end, we always sign the transaction with our own private key, and the rest of the process is the same. So let's see what happens if we try this logic. So last video we were left off with 4,750 Satoshis. So we're going to try each of these different scenarios one at the same time. So let's see what happens if we input an address to a different wallet and we send an amount which gives us back some change amount. So here we got a successful transaction ID. We're gonna open that amount in a Explorer. And we're gonna see the transaction that got generated by our wallet. As you can see here, we sent 1,000 Satoshis to a wallet which is not our own deposit address. And then here in the end we have our change output, which sends the remaining 3,523 Satoshis back to ourselves, which, as you can see here, it is exactly our remaining balance. So the code path that we just went through is the one below here. That's the last one. Now we can also see what happens if we try to send money to ourselves. Let's put again 2,000 Satoshis. Here we had a successful transaction. Here we can see that although we did have enough money for us to create a change output, in this case we're actually sending a single output which sends all the money to ourselves except just the sufficient amount of fees that are needed for this transaction to be broadcasted and mined. Now the last case we want to test out is what happens when you're trying to send a certain amount to an address that does not leave enough money for a change address. So let's get back this address here. And now if we want to make sure that there's no money left over, I'm going to send an amount which once I add the estimated number of Satoshis as the fee, I know that we're not going to be left with enough money to send a change amount to ourselves. That is because 2,900 just gives you, if you spend around 200 satoshis for the transaction itself, then you're left with 3,100, and then you have 2,900. That leaves over 200, around 200 satoshis as a change amount. However, that amount is below the dust limit, and we're not going to get it back ourselves. It just goes to the miner fee. This is the new transaction. Let's see that one on the Explorer. Okay, so here we can see it. We actually sent all the money to a single output. There was no secondary output, no change amount. And now if I go back to our wallet and I refresh the page, you can see that we have 0 satoshis, which we have just withdrawn the full amount to a separate wallet. That completes the 3 different scenarios that we had here. And I'm just going to very briefly see what happens when I try to send a transaction with insufficient balance. We get the error saying that we have insufficient balance. Now also let's see what happens if I try to send an amount which is below the dust limit. There it goes, output amount below dust limit. So that means that every normal scenario where we might want to send money in different types of situations, they're all working. Our wallet is able to handle all of them. And at the same time, all of the transactions that we're generating are actually using almost exactly the minimum amount of fee that they can use, which is very close to 1 Satoshi per byte. Now that essentially completes the implementation of our wallet. Now we have a full Bitcoin Cash wallet, single address, which allows us to deposit money, hold money, import and export a backup of the wallet in the form of a private key in wallet import format, and it allows us to spend that money in all the normal ways that we might expect the wallet to work. Now that essentially completes part 7 of this tutorial, and see you on the next video for a couple final remarks.